Welcome to the deep dive. Today, we're going to be taking a look at some research that you sent over about this physics theory called Fibonacci SMF RVS,
Yeah,
which initially it was developed to explain nuclear stability.
right.
But you shared some research about how it might also change how we understand chemistry.
Yeah, that's the really exciting part, is that it suggests that we may be able to manipulate chemical reactions in ways that we never thought possible
Okay.
by tapping into the energy of the vacuum of space itself.
Well, in the vacuum of space, I thought that was like empty. How could that possibly impact something as tangible as chemistry?
That's where things get really interesting.
Okay.
The theory proposes that what we perceive as empty space is actually teeming with energy
Okay.
in the form of complex fractal wave patterns.
Mm-hmm.
These fractal vacuum waves, as they're called, could be interacting with matter at a
Okay.
very fundamental level,
Mm.
including those tiny electrons that determine how atoms bond together.
So maybe not so empty after all. But how does a wave, even a fancy fractal one, influence how electrons behave? I mean, electrons are particles, right?
Right. But according to quantum mechanics, particles can also exhibit wave-like behavior.
Right.
And the theory suggests that the energy levels of electrons in atoms are actually determined by how they resonate with these fractal vacuum waves.
So these fractal waves are like a hidden blueprint for the structure of matter. That's a pretty radical idea.
It is, and if it's true, it means we might be able to tweak the energy of these vacuum waves to influence how electrons interact
Okay.
and ultimately control chemical reactions in a whole new way.
Now that's what I call a game changer. But how would we even begin to manipulate something as ethereal as a fractal wave?
That's where the concept of subtle magnetic fields comes in.
Okay.
The research suggests that carefully crafted magnetic fields could act as a kind of tuning fork,
Interesting.
influencing the resonance patterns of these fractal vacuum waves.
So we're talking about using a magnetism to literally shape the energy landscape of the vacuum. That sounds like something straight out of science fiction.
It might sound far-fetched,
Yeah.
but the researchers have laid out a theoretical framework for how this could be achieved, even outlining specific ways we could test these predictions in a lab setting.
All right, I'm hooked. But before we get into the experimental details, can you give me an example of how this could be applied in the real world? Something that would make this mind-blowing concept feel, well, a little less mind-blowing.
Let's take the example of ammonia synthesis, the process used to create the ammonia that's vital for fertilizer production.
Okay.
It's an incredibly energy-intensive process, but this new theory suggests we might be able to make it significantly more efficient.
More efficient fertilizer production. Now that's something I can get behind. Tell me more.
Imagine being able to manipulate those fractal vacuum waves, using these subtle magnetic fields to lower the energy barrier needed for nitrogen atoms to bond together and form ammonia. We could potentially cut the energy requirements of the process drastically.
Wow. That would be a game changer, not just for the fertilizer industry, but for global food production and sustainability as a whole.
Exactly, that's just one example.
Yeah.
The potential applications of this theory are vast, spanning everything from the development of new materials to breakthroughs in medicine.
Okay, color me intrigued. So how do we get from a mind-bending theory to actually manipulating these fractal waves in a lab? What kind of experimental setup are we talking about?
Well, the researchers propose using a system of electromagnetic coils to generate a very precise magnetic field environment. It's not just about creating a magnetic field, it's about shaping it with incredibly specific boundary conditions.
So you're saying it's not like just sticking a bar magnet next to a beaker.
Right.
We're talking about a much more controlled
Exactly.
and sophisticated approach.
Think of it like sculpting with magnetic fields.
Okay.
The researchers believe that by carefully configuring these coils, we could create areas of high and low energy within the vacuum itself, influencing those fractal waves we talked about.
Okay, I'm trying to wrap my head around this.
Yeah.
So by manipulating these magnetic fields,
Right.
we're essentially creating pockets of energy within the vacuum that can either enhance or inhibit certain chemical reactions.
Precisely.
Okay.
It's like setting up a microscopic energy landscape that influences how electrons behave and how atoms bond together.
So going back to that ammonia synthesis example, how would these magnetic fields actually make the process more efficient?
Remember that incredibly strong triple bond between nitrogen atoms that makes it so difficult and energy intensive to break them apart?
Yeah.
Well, the theory suggests that by creating specific nodes of energy within the vacuum, we could weaken that bond, making it easier for the nitrogen atoms to react and form ammonia.
So it's like these magnetic fields are creating little weak spots in the armor of those nitrogen molecules,
Yeah,
making them more susceptible to reacting.
that's a great analogy. Okay. And the researchers have actually developed a theoretical framework for how to calculate the exact magnetic field configurations needed to achieve this effect.
Okay.
It involves solving a complex partial differential equation, or PDE, that describes the behavior of those fractal waves under the influence of these magnetic fields.
A complex PDE. So we're not just talking about some back-of-the-envelope calculations here. This is serious math.
Oh, absolutely. This theory is pushing the boundaries of both physics and mathematics, but that's what makes it so exciting.
Okay, let's say we have brilliant mathematicians who can solve this PDE and figure out the perfect magnetic field recipe. How do we actually create these fields in the real world, and how do we know if it's even working?
That's where things get really challenging. We're talking about generating incredibly precise magnetic fields at a microscopic scale. It would likely involve advanced nanofabrication techniques and incredibly sensitive measurement tools.
So not exactly something we can whip up in a high school science lab.
Definitely not. But the researchers are optimistic that as technology advances, we'll have the tools needed to put this theory to the test.
So it's still very early days. But if they're right, this could be absolutely revolutionary. We're talking about rewriting the rules of chemistry, potentially unlocking new possibilities in everything from energy production to medicine.
It's truly mind-boggling to think about the potential impact, but it's important to remember that this is all still theoretical. There's a lot of research and experimentation that needs to be done before we can say for sure whether this theory holds up.
That's a good point. But even if it turns out to be a long shot, the very idea that we might be able to manipulate the vacuum of space to influence chemical reactions is incredibly inspiring.
Absolutely. It shows the power of human curiosity and the endless possibilities of scientific exploration.
Okay, before we get too carried away with the sci-fi implications, let's bring it back down to Earth for a moment. What are some of the practical challenges researchers would face in trying to test this theory in the lab? I imagine it's not going to be easy.
Oh, there are definitely some major hurdles to overcome. One of the biggest challenges would be detecting the incredibly subtle effects of these fractal vacuum waves on chemical reactions. We're talking about measuring energy changes on a quantum scale,
Right.
which requires extremely sensitive instruments and meticulous experimental design.
So it's not like we can just throw some chemicals in a beaker wave a magnet over it and see if anything happens.
Not quite. It would require carefully controlled experiments that can isolate the effects of the magnetic field on the fractal vacuum waves from all the other factors that can influence a chemical reaction.
That sounds incredibly challenging. What about the practical aspects of scaling this up? Let's say we can demonstrate this effect in the lab. How do we go from manipulating a handful of atoms to something that could actually be used in industry?
That's another major hurdle. Scaling up any new technology is always a challenge. But this one is particularly tricky because it requires such precise control over magnetic fields at a very small scale. We might need to develop entirely new manufacturing processes and materials to make this technology commercially viable.
So even if the science checks out, there is still a lot of engineering and logistical challenges to overcome. But let's say for a moment that we can overcome these challenges. What kind of future could this unlock? What are the potential benefits of being able to manipulate fractal vacuum waves on a large scale?
The possibilities are truly mind-boggling. Imagine a world where we could precisely control chemical reactions, reducing waste, minimizing energy consumption, and creating entirely new materials with unprecedented properties. We could revolutionize industries like manufacturing, energy production, and medicine.
Okay, now you're going to be really excited. Give me some concrete examples. How could this technology change our lives in a tangible way?
Well, for starters, we could potentially develop much more efficient and sustainable ways to produce fertilizers, which could have a huge impact on global food security. We could also create new types of catalysts that accelerate chemical reactions with incredible precision, leading to breakthroughs in everything from drug development to clean energy technologies.
That sounds incredible. But what about the potential downsides? Are there any risks associated with manipulating something as fundamental as the vacuum of space?
It's certainly something we need to approach with caution. Anytime we delve into new realms of science and technology, there's always the potential for unintended consequences. That's why it's crucial to proceed with rigorous testing, careful risk assessment, and open discussions about the ethical implications of these advancements.
So while the potential benefits are enormous, we need to make sure we're not rushing into anything blindly. We need to consider the long-term impacts and ensure that this technology is used responsibly.
Absolutely. It's essential to have a holistic view that takes into account not just the scientific advancements, but also the societal and ethical implications.
Well, this deep dive has certainly been an eye-opener. The idea that we might one day be able to manipulate the very fabric of space to control chemical reactions is both exhilarating and a bit daunting. It just goes to show how much we still have to learn about the universe and the power of human ingenuity to unlock its secrets.
It's a reminder that we're living in an era of incredible scientific discovery, and the possibilities for the future are truly limitless.
Thanks for joining us on this deep dive into the mind-blowing world of fractal vacuum waves and the potential to revolutionize chemistry. It's left us with a lot to think about and a sense of wonder about what the future holds.